Greetings, this is Chemistry with Nav. In this video we're going to do something a little bit different. I've been working with some students recently and I found myself saying you're meant to know this about quite a lot of different things. So I thought we'd make a little video. It may be longer than usual. It's aimed at AS students and first year IB students about things you're supposed to know. So let's make a start. With the elements, there are 7 diatomic elements that you are supposed to recognize and that you would have to know if you were writing a chemical equation that they were diatomic. Diatomic meaning that they go around as 2 atoms, so pairs. And these are Hernophclabri, which is H, N, O, F, Cl, Br and I. And apart from the hydrogen, if you look at the top right hand side of the periodic table, you'll see a sort of upside down L going NOF and then coming down Cl, Br and I. So Hernophclabri tells you that you have these formulae, H2, N2, O2, F2, Cl2, Br2 and I2. But this is when the substance that you're talking about is a pure element. If this is now being used in some sort of compound, then yes, it doesn't have to go around in pairs. As we would know from things such as water and ammonia. The definition, don't forget, of an element is a substance that's made up only of one type of atom. Okay, so we've got 7 diatomic elements there. The next thing I want to look at is acids and bases. Now, one of the newer concepts that you come across is the idea of an acid as a proton donor. But what that means is that an acid produces H+ ions in solution. So if I take some sort of substance and I try to dissolve it in water, then I will get free H+ ions if that substance is an acid. If we have a base, that means that we have a proton acceptor. And I'll do a little diagram in a moment about showing this proton donating and this proton accepting. Then we have an alkali. And an alkali is basically a soluble base. So all alkalis are bases, but not all bases are alkalis. And it's a soluble base, or it's something that produces OH- ions, hydroxide ions, in aqueous solution. And one little thing actually that might help you with what a base is that metal oxides and hydroxides are bases. And then moving on to salt. Oops, wrong one. A salt is formed when the hydrogen ions, the H+ ions, in an acid are replaced by metal ions or ammonium, which is NH4+. Okay, and this brings us on to acid reactions in which you make salts. And this is in another video which I released I think about a month ago or so, and it comes down to mash, bores and corks. And I use this system because it helps you to work out what the products would be in an acid reaction, because a metal plus acid gives you salt plus hydrogen gas, a base or an alkali plus acid gives you water and salt, and a carbonate plus an acid will give you water, carbon dioxide and salt. So the major difference being between the metal and the base, that if you use the metal you get a hydrogen, and if you use a base, which is a metal oxide or a metal hydroxide, then you'll get water produced with your salt. But then we need to look at salt names, and salt names are derived from the acid that was used in the reaction. So if we look at the acid and we look at the anion in the acid, which is the negative ion, then we will find the salt name. So if we use HCl and we take off the H+, which is the cation, then the anion is Cl-, and the Cl- ion is the chloride ion, so the salt name is always something chloride. If we use HNO3, nitric acid, the anion here is NO3-, and the NO3- ion is nitrate, so the salt name is something nitrate, for instance potassium nitrate. If we use sulfuric acid, then the anion is SO4-2-, and the SO4-2- ion is a sulfate ion. And the last example, ethanoic acid, CH3COOH, the anion there, it's the H at the end that gets removed, so it's CH3COO-, and that is called the ethanoate ion. So that comes up in a bit of organic chemistry. If you react ethanoic acid with let's say sodium hydroxide, then you'll get sodium ethanoate. These acids, you must know their formulae and their names. It's very important. So we've got hydrochloric acid, nitric acid, sulfuric acid, and ethanoic acid. And lastly on this topic, just to look at the neutralization reaction. If we take some example of a full equation for a neutralization, we might take HCl, hydrochloric acid, and react it with sodium hydroxide, which would give sodium chloride and water. These are aqueous except for the water, which is liquid. If I want to convert that into an ionic equation, then I need to get rid of any spectator ions, and spectator ions are ones that have literally done nothing. So the Cl- ion on the left hand side in the hydrochloric acid has turned into a Cl- ion on the right hand side, and they're both aqueous. The sodium ion in the sodium hydroxide is aqueous, the sodium ion in the sodium chloride is also aqueous. That has done nothing. So the only thing that's actually reacted is the H+ aqueous and the OH- aqueous. Those were ions to start with, and now they have formed the covalent liquid water. And that is the neutralization reaction. H+, which is your acid, as we said from the definition earlier, OH- from your alkali, giving you water. And an ionic equation, one that removes any spectator ions. Okay, so next is some common anions. There are certain things that you would be expected to know the names of. CO3 2-, SO4 2-, NO3-, PO4 3-, Cl-, Br-. I think that's enough for now. So hopefully you will know some of these. Starting at the top, we have carbonate, sulfate, nitrate, phosphate, chloride, and bromide. And note here, anything that ends in ATE means with oxygen. So the carbonate ion is both carbon and oxygen because it ends in ATE. Sulfate, sulfur and oxygen because it ends in ATE. But if you have IDE, it means by itself. So the chloride, the bromide, and another good one, O2-, which is oxide, they are all that element by itself. So chloride, chlorine only, bromide, bromine only, oxide, oxygen only. So make sure you are familiar with those. The next small thing is the idea of aqueous versus liquid. Aqueous means dissolved in water. That means you have a mixture. You have, let's say, sodium chloride, which is a solid. You get some water involved, and that makes sodium chloride aqueous. So that's if you have, let's say, a glass of water or a pan of water on the stove, and you add some salt to it, some common salt. That would be salt dissolving in water. It becomes a solution. But if you have a liquid, this means you have melted it, or perhaps you've condensed it from a gas. A little brain freeze there. Right, so if you have a liquid, that is now just a pure substance. And if I start again with sodium chloride solid, then in order to make it into sodium chloride liquid, I heat it. And note, this is heating, not combustion. The major difference is oxygen. If I'm combusting something, that means I'm reacting it with oxygen. If I am heating something, I'm just changing state, so going from solid to liquid to gas is what happens as you heat something. Next up is types of bonding. Now, I'm not going to go into a full review of all types of bonding, but what I want to do is show you that it's possible to spot the type of bonding from the substances present, because covalent bonding occurs between a non-metal and a non-metal. And our example of that could be ammonia, NH3. So that's going to be a covalent substance. If I have ionic bonding, then that's between a non-metal, which will form a negative ion, and a metal, which will form a positive ion. And the example we've been looking at already is NaCl, because that is made up of Na plus and Cl minus, where the sodium atom has given one electron from the outer shell to a chlorine atom, which makes Na plus ion and Cl minus ion. But that's because it's a non-metal and a metal. And if you're looking at metallic bonding, then that's between two metals. And that could be in a pure metal, or it could be in an alloy. The last couple of things. Let's look at enthalpy change. Here, the idea of something being exothermic means that it gives heat out to the surroundings. But quite often in exams, you're actually asked to give examples of exothermic and endothermic reactions. So combustion would be a very good one for an exothermic reaction, remembering that your delta Hc, your enthalpy change of combustion, is defined as the energy change when 1 mole of substance is combusted completely in oxygen at standard conditions. You could also have neutralization. So whenever you have an acid and an alkali coming together in solution, there is an exothermic reaction. And the enthalpy change of neutralization is the enthalpy change when 1 mole of water is formed in the reaction between an acid and an alkali at standard conditions. For endothermic reactions, there are far fewer of these, so trying to remember a couple of examples is useful. Thermal decomposition is one, and that's, for example, calcium carbonate going to calcium oxide and carbon dioxide, which is normally something done at GCSE, but that requires a lot of heat, and if it requires a lot of heat input, then that is an endothermic reaction. And another example would be photosynthesis. And then the last thing I want to look at is oxidation and reduction. whenever you have a reduction reaction, you must also have an oxidation reaction somewhere going on. But something that happens quite regularly is that you learn about the fact that oxidation is loss of electrons and reduction is gain of electrons. So let's just write that in. So that's something that we learn from GCSE because of electrolysis, and we're looking to see whether something is oxidized or reduced. But now, when you have oxidation numbers or oxidation states, we can actually have a slightly simpler explanation as well, where oxidation is a rise in oxidation number. So if you have an element such as sodium, and starting with oxidation number 0, ending up as Na+, which has oxidation number +1, then that means it has been oxidized because the oxidation number has risen or increased. And reduction is a reduction in oxidation number. So that would be for an element such as chlorine, which might start as 0 as the reactant, but then when it makes the product, it may make a Cl- ion, and that's a -1 oxidation number. So going from 0 to -1 is a reduction, therefore you have a reduction. But let's also remember the very simple idea of oxidation, which sometimes gets lost at a higher level. Oxidation is gain of oxygen, and reduction is loss of oxygen. Okay, well that is everything I wanted to look at today. Please feel free to ask any questions or request any extra videos. Otherwise, have a good day.